So I'm going to title this particular section or this discussion part is the transition from DFS to DFT. We're going to move from, basically we're going to use the framework to move from here to the, so and again we're going to look at number of results. I want you to pay close attention and then review them multiple times, because this is not something that you will fully be able to understand in the first instance. So it will take several times for us to read this particular method and look at it. Okay, the first one. Remember, I'm talking about a Fourier transform. I'm going to a discrete Fourier transform. Okay, so go back to a very fundamental result. What is the condition for the existence of the DTFT? It must be square summable. The sequence must be square summable. Okay, so that was a condition that we saw. Absolutely summable, not square summable. So this is absolutely summable. Okay, and we also saw that if you had square summable, we will get a discrete time Fourier transform. But it will be convergence not in the uniform sense, but it will be a mean square convergence. Mean square convergence. Convergence of the discrete time Fourier transform. Okay, nothing new. Then we also saw that there were special cases where the discrete time Fourier transform existed. Special case. This is for periodic sequences. Periodic sequences in time. Okay, and the corresponding discrete time Fourier transform had Dirac delta functions. Okay, so basically we allowed those Dirac delta functions to come into play, and that is how we allowed the Fourier transform. But in this particular case, these do not satisfy either absolute summability or square summable. Okay, so these are not absolutely summable because they are infinitely long sequences. Okay, absolutely summable. Neither will they be absolutely not square summable either. Square summable. Okay, absolutely summable means summation n equal to minus infinity to infinity modulus of x of n. This is less than infinity. Square summable means summation n equal to minus infinity to infinity x of n magnitude squared. This is less than infinity. Basically, that's the final. So those were the two conditions that we had. Now, a third result that we have already used in discrete time Fourier transform is going to come and play a very important role for us. Okay, if I have a sequence x of n, periodic sequence, which is given by the following. Okay, k is the summation over k, a subscript k e power j omega k n. So these are complex sinusoids which go from minus infinity to infinity. Okay, we said that of course these will not satisfy either absolute summability or square summability, and therefore we are going to invoke this special case. And we said that x e of j omega has the same number of terms, right? Summation over k. We have the same scale factor. We will get a scale factor of 2 pi and delta at those delta functions at those places where the complex sinusoids are present. Okay, now this is a correct representation if you are looking in the region 0 to 2 pi. But we know that xe of j omega has got periodicity and it has got period with period equal to 2 pi. So we have to represent this in a more accurate fashion to say that any shift of 2 pi is also okay, 2 pi r. And that will basically mean that r can go from minus infinity to infinity. Okay, r is equal to minus infinity to infinity. So basically you have whatever was the original summation of k terms, those terms are present. You get delta functions wherever the complex sinusoids are. There is a scale factor of 2 pi, and in addition you will, the same thing what you see between 0 and 2 pi will repeat for every multiple of 2 pi. Okay. So this is a very, very important result. Okay. Now here is where we are going to start bridging between the two. So far what we have said, everything is regarding DTFT. Okay. DTFT. Now I am going to switch to DFS. DFS says that if x tilde of n is periodic with period equal to n, okay, then we have the discrete Fourier series x tilde of n. This is discrete Fourier series. Okay, whatever we have said earlier was Discrete-Time Fourier Transform. Okay, and this will be x tilde of k. And we know that the representation of x tilde of n can be done using the synthesis equation, which is given by 1 over n summation k equal to 0 through n minus 1 x tilde of k wn. Is it minus nk or nk? Minus kn. Okay, make sure that we don't make a mistake in terms of the representation. So this, when you write it with w, it will come with a minus sign. Okay. Now comes a very important observation. What do you have x tilde of n is a periodic signal. It is a sum of k or a sum of n complex sinusoids. Okay, and it has got a scale factor of 1 over n. Now look at the result that we obtained earlier. So this periodic signal x tilde of n can have a discrete Fourier series representation. That's what we have here. But because it's got the same structure as the signal in the previous column, we can also write down a discrete time Fourier transform representation for the signal. Okay, same signal, periodic signal, and but the discrete time Fourier transform will have delta functions. Okay, so write down the let's call this as xe of j omega and we'll write it with a tilde function because that's x tilde of n. The DFS is x tilde of k, but what we are writing is discrete time Fourier transform x tilde. Okay, so by looking at comparing it with the previous section, I hope you will be able to write down x tilde e of j omega will have the k sinusoids, k equal to 0 through n minus 1. There will be a scale factor of 1 over n and there is an additional scale factor of 2 pi. 2 pi divided by n is the scale factor, and the coefficient x tilde of k becomes an additional scaling term. Then will come the delta functions, r equal to minus infinity to infinity delta of omega minus the, where are the frequencies located? They are located at multiples of 2 pi by n multiplied by k. So those are the places where the discrete Fourier series coefficients are evaluated. K, these are the kth harmonic multiple kth harmonic, and you can also get all of these things shifted by 2 pi r. So basically the same sequence gets shifted by 2 pi r. Okay, now notice that there is a very important step that we are going to be looking at. X tilde of k is periodic with period equal to n. Okay, now 2 pi by n times k, k equal to 0, 1 through n minus 1. Notice that when you cross n minus 1, you get back the original sinusoid. Okay, so we find that the sinusoids are also periodic with period equal. So what we basically, if you add 2 pi r, that will also be another multiple. Okay, so in other words, what we are saying is we are taking the period from 0 to 2 pi. Okay, this is 2 pi by n, this is 2 pi by n times 2, and so on. And then when you go past this point, this value is 2 pi by n into n plus 1, n plus 2, and so on. So basically the delta functions are uniformly spaced even when you repeat it with a period of 2 pi, shifted by multiples of 2 pi. So therefore, this equation can be written in a compact form in the following manner. Summation k equal to minus infinity to infinity. The scale factor is 2 pi over n for all of these delta functions, multiplied by the corresponding DFS coefficient x tilde of k, delta of omega minus 2 pi by n times k. What we have done is we have combined these two terms into a single term that captures it, because basically whether you look at it between 0 and 2 pi and then shift it, or look at it as a series of delta functions, all of them are uniformly spaced and they are all at multiples of 2 pi over n. Okay. Now I want you to notice the following observations. Now the discrete time Fourier transform must be periodic. Okay, so make sure that you verify for x tilde e of j omega. First is periodicity, that it is periodic. Okay, then the second one is that it's periodic with period equal to n. That also will be true. You can verify that both of these are satisfied. So this is a valid discrete time Fourier transform. Okay. Now comes a second very important result that I want you to follow along. Okay, I'm going to introduce for you the periodic impulse train. If you remember, we saw it in our discussion on sampling. Right at the early stage of our course, we looked at sampling. So periodic impulse train. Periodic impulse train says there is one delta function at 0, and then there are n minus 1 zeros, and then another delta function. So basically this one is summation r equal to minus infinity to infinity delta of n minus Rn. Okay, good for you to sketch. That is 0, n minus 1 zeros, and then you have another one. Okay, so just for labeling them, 0, 1, 2, this is n minus 1, this is n, this will be 2n, and so on. So basically every multiple of n you will get a delta function. That is a periodic impulse train. Okay, this is not Dirac delta, it's a unit impulse, right? So basically the height is equal to 1. The height is equal to 1. Okay, now take one period of this and compute the discrete time Fourier series coefficient P tilde of k. Okay, apply the analysis equation. Delta function is defined only at n equal to 0, and therefore what you will get is P of k equal to 1 for all k, for all k. Okay. So now look at the expression that we have previously. If x tilde of n is periodic, we said that you can get a discrete time Fourier transform representation. This is a periodic signal. So what is the corresponding discrete time Fourier transform? Okay, no problem. We will call this as equation number 1. Okay, so from equation 1 on the previous page, with all the DFS coefficients equal to 1. Okay, so P E of j omega will be given by summation k equal to minus infinity to infinity 2 pi by n delta functions omega minus 2 pi divided by k. Okay. Now another result. Okay, so basically we are developing. So this is equation 2. Okay, now a third result. If I convolve x of n with this delta function p of n, this periodic impulse train, then what we get is x of n convolved with summation r equal to minus infinity to infinity of delta of n minus Rn. Okay, this is nothing but summation r equal to minus infinity to infinity. Wherever there is a delta function, you will shift it to that point. This will be x of n minus Rn. X of n minus Rn. Okay. Now, what I want you to think about is a very important observation here. Okay. So, if I have a finite length sequence x of n and I convolve it with a periodic impulse train, now what happens? It will become a periodic signal. So, just as a illustration, this x of n is a finite length sequence, total length n equal to 8, okay, n equal to 8, n equal to 9, number of samples, okay, and I'm going to convolve it with a period with a periodic impulse train, which is given by p of n is equal to summation r equal to minus infinity to infinity delta of n minus 12r. Okay, I'm going to shift it. So now when I convolve x of n with p of n, then what I get is a periodic signal. Okay, very, very important. Okay, don't ignore the sequence that's on the figure that's on the right hand side. Focus on the one that's there. So you can see how you get a periodic sequence from a periodic sequence by convolving that. Okay, we will use that result in our discussion. So this is a periodic signal. This is a periodic signal. Okay, so I'm going to call this as x of n tilde. What is the period? The period is equal to n. That's the spacing between the impulse train. Okay, so now if this is the expression for the underlying periodic signal, then the discrete time Fourier transform x tilde e of j omega will be equal to x e of j omega. Convolution in time will become multiplication. This will be p e of j omega. Okay, and maybe we can even call it as tilde because this is a periodic signal. Okay, so now write down the expression here. This will be equal to x e of j omega. P e of j omega, we are going to multiply with this summation k equal to minus infinity to infinity 2 pi by n delta of omega minus 2 pi k. Okay, very, very important expression that we have. Notice this is not convolution, it is multiplication. So, which means that only where the delta function is non-zero, you will get a output in terms of the product. Everywhere else, it will go to 0. Okay, so we can now say that x tilde e of j omega is given by summation k equal to minus infinity to infinity. When you multiply x e of j omega, that is a continuous function of omega, but when it multiplies with the delta function, then you only will have non-zero coefficients where the delta function exists. So, it will be 2 pi by n, the scale factor, x e of j 2 pi by n times k. That is where the delta function, sorry, this must be 2, I have been writing it incorrectly. It is 2 pi by n times k, right? Yeah, I am sorry about that. Please make that correction. This should be 2 pi by n times k. So, those are the places where it will, and then of course the delta function is there. Okay, delta of omega minus 2 pi by n times k. Okay, this is result number 3. Okay, now compare 1 and 3. 1 and 3. What we have done is obtained two expressions for the discrete time Fourier transform of the periodic signal x tilde of n. Okay, two independent expressions. So, let us just copy and paste equation number 1. This is x tilde e of j omega. Okay, let us just copy this one. Edit, copy. Okay, this was equation number 1. Okay, now what can you tell me? These are identical equations. The only thing that we can observe is that the discrete time Fourier series coefficients x tilde of k are equal to the discrete time Fourier transform sampled at uniformly spaced points. Okay, x e of j omega sampled at 2 pi by n, 4 pi by n and so on. So, what we find is that the discrete Fourier series coefficients are nothing but the discrete time Fourier transform and sampled at omega equal to 2 pi by n times k. That is what we get, what we have here. Okay, this is a very, very important result. Okay. Now, what did we do? We had a periodic signal. We had a periodic signal for which we computed the Fourier series coefficients, and from that we obtained a discrete time Fourier transform representation. Independently, we took one period of the periodic signal, multiplied it with a periodic impulse train, obtained the periodic sequence, and then we showed that the discrete time Fourier transform of the periodic signal is actually related to the discrete time Fourier transform of that one period of the periodic signal x e of j omega, that is sampled at uniformly spaced points. Okay, so let us write this down. It's a very important result. So the observation, the final conclusion is that the periodic sequence x tilde of k, the periodic sequence x tilde of k, this is the discrete Fourier series coefficients, DFS coefficients, okay, are identically equal to or can be interpreted as equispaced samples, of the discrete time Fourier transform of x of n, which is one period of x tilde of n. These discrete Fourier coefficients are of the periodic signal x tilde of n. Okay. What is the significant result that we have obtained here? Okay. Remember, when we started our discussion on this chapter, we said that we would like to get a compact representation of a finite length sequence, which is x of n. Now, if you can visualize x of n as one period of a periodic sequence, no problem, just think of it as one period of a periodic sequence, then the periodic sequence does not require a continuous function but requires only the Fourier series coefficients. And how many Fourier series coefficients are there? Exactly n. So, what we are going to say is that any finite length sequence can be visualized as one period of a periodic sequence. And that periodic sequence will have Fourier series coefficients which are uniformly spaced samples around the unit circle of the discrete time Fourier transform. And that is sufficient for us to represent the signal. Okay, so it's a very, very important statement that we have made, and this is going to be the foundation on which the discrete Fourier transform is going to be built. Okay, so let us summarize all that we have said so far. So here is a summary, just so that you can review the chapter, the description that is given for you, given in the textbook, but this is also a way for us to completely keep in mind what we have been talking about. Okay, x tilde of n is a periodic signal for which we can compute discrete Fourier series coefficients given by x tilde of k. Okay, and for this we can also obtain the discrete time Fourier transform. I'm going to call it x tilde e of j omega, using the property that periodic signals can have the discrete time Fourier transform when you allow delta functions. This is equal to summation k equal to minus infinity to infinity 2 pi by n x tilde of k delta of omega minus 2 pi by n times k. Okay, this is the discrete time Fourier transform. Okay, and then we also introduced the periodic impulse train, that this x tilde of n can be viewed as one period of a signal convolved with the periodic impulse train, where this periodic impulse train has got a period equal to n. Okay, so p tilde of n is equal to summation r equal to minus infinity to infinity delta of n minus Rn. Remember that there is a delta function every n samples. Okay, and this has got a discrete time Fourier transform representation, p tilde e of j omega, which is given by summation k equal to minus infinity to infinity 2 pi by n all the coefficients are equal to 1, the discrete Fourier series coefficients, and so basically what you will get is delta of omega minus 2 pi by n times k. Okay, this was a result that we obtained. So from here we also write down that x tilde e of j omega, the discrete time Fourier transform, will be x e of j omega multiplied by p tilde e of j omega. Okay, so this is a important result, and by comparing these two, okay, this is equation number 1, equation number 2, you can substitute for p delta, we then get from 1 and 2, we get the result that x tilde of k, the discrete Fourier series coefficients, are nothing but uniformly spaced samples around the discrete time Fourier transform. Okay, omega equal to 2 pi by n times k. So this is nothing but x of e power j 2 pi by n times k. Okay, so this is the another important result that this is what we have obtained so far. So what else can we write down in terms of a summary? Okay, x of n, this is equal to the periodic signal within the period, first period, n greater than or equal to 0, less than or equal to n minus 1. So basically that's the period that we are looking at, and is 0 outside. X tilde of n goes from minus infinity to infinity, but what you are saying is x of n is only one period. That's what we saw here, right? One period of the periodic sequence, and then you get the periodic signal. Okay, so the important thing is, what is the relationship between x of n and x tilde of n? And this then also ties into the relationship that we have obtained, which says that x tilde of k, x tilde of n is represented by x tilde of k, x of n is represented in terms of x e of j omega, and x tilde of k are uniformly spaced samples of x e of j omega. Okay, so let's write that down. So x tilde of k can be obtained as equispaced samples, of x e of j omega. Okay, and how many samples do you get? Exactly equal to number of samples equal to n. Okay, now one last statement so that we will complete the discussion. Now remember, we convolved x of n with a periodic impulse train. And the period that we chose here was the period of the impulse train was 12. The period of the non-zero portion of the signal was 9. Okay. Now, if you had not chosen a periodic impulse train with a sufficiently long period, then when you convolve the two, what will happen? These copies of these of x of n shifted versions will start to overlap. And that is what you're seeing here. Okay, so this is a case where p of n is equal to summation r equal to minus infinity to infinity delta of n minus 7r. Okay, so what we are saying is the periodic impulse train must have a period which is at least as large as the finite duration signal. If not, then what you will get is a distortion. Okay, this is a distortion similar to aliasing distortion that we have seen before. There's basically overlap of images. So basically this would lead to distortion. Okay, and this is an undesirable one, and of course once there is a distortion of this type, no way can you say that I can compute the discrete Fourier series coefficients from the discrete time Fourier transform. Basically the signal is now completely distorted. So the last point that we want to add to our summary is the following statement. Okay, x tilde of k, Fourier series coefficients, are samples of x e of j omega, the previous statement, if n is sufficiently large. Okay, yes, you get it as uniformly spaced samples, but you must make sure that you get enough number of samples if n is sufficiently large. Otherwise, you will run into distortion, which will create a problem for us. Okay, so the conclusion, let me write it down and then we will stop with that. The conclusion is that for finite length sequences, we have the following relationship: x e of j omega. This is discrete time Fourier transform. For periodic signals, we have discrete Fourier series, which has a finite number of coefficients, x tilde of k. These two are the foundational results. I hope there is no confusion whatsoever. Okay. Now, this is what we are going to do. If I want to represent x of n, then from here I can obtain a periodic signal x tilde of n. Remember, I can convolve with a periodic impulse train. That will give me a representation which is x tilde of k, and this, as long as n is sufficiently large, can be obtained as x e of j omega, which is sampled at omega is equal to 2 pi by n times k. Okay, so this is the framework that is existing for us. I want x of n to have a compact representation. Normally what I would have said is take x of n, you can go to the DTFT. That's a continuous function. But because we have this underlying relationship with periodic signals, from x of n I can get x tilde of n, from x tilde of n I can get x tilde of k, which is related to this DTFT with the relationship. So here is the final statement. X tilde of k is sufficient to represent x of n. Okay, this is not a transform, this is sufficient to represent x of n. This is the heart of what we have been trying to do in today's lecture, to connect the discrete time Fourier transform, not the entire one but only samples, to the sequence x of n. So now what we are going to say is, we are going to define a new transform, the discrete Fourier transform, which will take only the samples of the DTFT and keep only that as the underlying result. So the discrete Fourier transform is going to be a finite length sequence mapped to a finite length transform. Okay, and that is going to be the core of what DFT is going to be. So if I were to write it as an expression, it would be something that you are already familiar with. The DFT, okay, DFT, no more tilde, x of k, is going to be given by the matrix D subscript n. Okay, so this is X equal to D subscript n of the lowercase vector x. Okay, so this is the DFT equation. The inverse DFT. Inverse DFT, again very similar to the DFS relationship. X is equal to dn inverse times x. Okay, x is a finite length vector, so make sure we write that down. This is n cross 1, this is n cross n, this is also n cross 1. Okay, and this is equal to 1 over n dn conjugate or Hermitian, both are the same because it's a symmetric matrix, times x. So a new transform which looks like the discrete Fourier series, but very important to remember that the discrete Fourier transform is a finite length sequence mapped to a finite length transform. It is not a periodic signal. What we are talking about is not a periodic signal. X of n is not periodic. So correspondingly, the discrete Fourier transform representation is not a periodic signal. However, there is an underlying framework where x of n is related to x tilde of n, which is periodic, and x of k is related to x tilde of k, which is periodic. So again, those are going to come into play when we look at the properties of the discrete Fourier transform. So we will pick it up from here in the next session and complete our study by looking at DFT and also an efficient implementation called the fast Fourier transform. Okay, so those are the things that are ahead of us, some very interesting signal processing algorithms, and that will be our concluding sessions. Thank you.